Okay. Now, if in case you want to add multiple layers and you want to define multiple activation functions, you can do some by this way. So this is the first layer we have defined, right? This is layer 1. Now let me create another layer. The process will be exactly similar. I'm having 4 neurons in this layer. Activation function is still ReLU. Okay. I am going to add another layer, third layer. At in this layer, I'm going to place total 2 neurons. Activation function is ReLU. Okay. So now I have created a neural network that will have total 3 layers. First layer 2 neurons, second layer 4 neurons, third layer 2 neurons, and each of my neuron will have an activation function as ReLU. Okay. Now I can get the model summary also. If I want to summarize my model, you'll see that, right? So what it says that I'm having total 4 layers, right? Why it is showing the 4 layer? Because I showed you the alternate way also of doing it, where I had 2 lines for creating layer and activation function.
So the input is also like a layer, right? That's why it's showing us 4.
No. Input is not layer. Here it is showing 4 because I showed you another step also for creating layer and activation function. So that step is also included. That's why it is showing the 4 layer.
Oh, okay. So if that was not there, it would not have shown. It would have shown only 3 layers.
Yes. Just focus on these 3. 2,
Okay.
4, 2. Okay.
So what is that none?
Where?
The output shape none.
Yeah.
None comma 2.
Yep. This means what? This means basically it says that we do not know how a number of rows is coming from input. All we know is the number of columns.
But isn't it the convention is rows followed by columns? So in input shape is equal to 4 comma 0 means 4 rows,
Yes.
unknown column. Right?
Yeah. So that happens in case of pandas. Here you just need to interchange.
You mean in TensorFlow we are interchanging where the column will be first and rows will be second?
Yes.
Okay. Got it.
Okay. Now, yeah. So now we learned how to create a neural network. Okay. And layers we have defined. We have defined the activation function. Next thing is what? Next thing come training, right? How do I train the model? So training is a process where it will figure out the optimal value of your parameters. With parameters, I mean W and B.
Yeah.
Right. So for that, I need to specify another step that is called compile. So what compile does is in compile we define that what kind of optimizer we want, what kind of loss functions we want to minimize, what would be my performance metric, right? So that thing we have to tell Keras beforehand, and accordingly it will do the optimization. Okay. So if I have to import compile, so for compile also we have also already seen, right? From where I can actually take compile. So let me first of all show you what are the different optimizers we have, right? So if I want to check the list of optimizers, I can check like this: Keras dot optimizer. Okay. I think okay. There's another syntax for that. Let me quickly refer that from documentation. Okay. See here, optimizer. So in Keras we have a lot of optimizers. For example, ADA delta, ADA grad, Adam, ADAMX. So these are the different optimizers. What we have in our theory class is SGD, stochastic gradient descent, right? Where we were finding the gradient of loss with respect to our parameters, and we will approaching toward minima. So that is nothing but that is called SGD. Okay, so let us take SGD from optimizer module, TensorFlow dot keras dot optimizers import SGD, right? So I have imported my SGD optimizer. Now this optimizer will have two arguments mainly, right? One is the learning rate, the other is the momentum. Learning momentum we haven't seen, right? So let's for now skip the momentum. We'll only deal with learning rate now. Okay. Now, similarly, we have functions for losses. We have functions for accuracy also, right? What we gonna see now is how we can add these three different input options in one go. Like we have seen here, right? How to create multiple layers and activation function in one go. Similarly, let's see here also. So my model is having a function called compile, and this compile will take argument optimizer. Here, let's define SGD. Okay, it takes another input which is loss. So this loss is our loss function. Here, let me take some optimizer functions, cross entropy. We have already seen it, right? So this is another loss functions, and this is for categorical problem, I mean classification.
It's a loss function name.
Yes, it's a loss function name. Like we have seen binary cross entropy, right? So similarly, sparse categorical cross entropy is another loss function, right? And matrix is what we want to define the performance of our model by accuracy. The accuracy it will have in test data, right? So we have given all this input. Till here, any question, any confusion you are having?
Yeah, I think, I didn't understand this optimizers part,
Yep.
why we are using it. You did explain it with some WNV, but it was not clear to me.
Okay. Okay. So typically any machine learning problem, what we want is we want to get the optimal value of B and W, right? We initialize our model with some random value of W and B.
Okay.
Correct. Now we need to take the help of optimizer to reach from those random value to the optimal value of W and B.
You mean to the minima? To mean to that in that curve where we reach to
Yes.
that bottom, right?
Yes. Yes.
Okay.
That value of W and B that will minimize my loss. Right. So for doing that task, we are having a lot of optimizers. In this particular case, I'm using one such optimizer, which is called stochastic gradient descent, SGD.
Because
Okay.
that's the example also we took, right? To understand that.
Yes.
Yeah,
Yes.
that's why you're using that here.
Yes. I could have taken some other also. There are a lot of optimizers, right? I already I showed you some optimizers, right? So I could have taken some other also. But here I have taken SGD because we have already seen it. So we know the theory part of SGD, how SGD works.
Yeah.
Okay. For performance, I have defined accuracy, and loss is the sparse categorical cross entropy. It is similar to binary cross entropy. There's slight difference, but we can, for now we can treat it as a black box. Okay, it's just
What
nothing
does
but
compile do then? What is compile doing?
compile means it is compiling all of this input, and it will inform model why when model will go for training.
Oh, so is it going to tell the model that, oh, because you're going to be using optimizer SGD,
Yes,
and the
yes,
loss function that you're going to be using will be the sparse,
yes,
and the metrics will be calculated based on this accuracy thing, right?
yes, exactly, exactly. Yeah. So these are the constraint we are putting, right?
Yeah, and then if you go up, right, there's this output called params. So
Or
from where did we get that those numbers 6, 10, and 12?
6, 10, and okay. This one you're talking?
Yeah, the 6, 12, and 10, right?
Yeah,
Dense 1, dense
yeah,
2. So how did we get that?
yeah. Actually, I was thinking to cover this in theory class, but yeah, I can take it here also. See, here in my dense layer, I'm having total two number of neurons, right?
Yeah.
And I'm having input. That input is having four features, right?
Yeah.
So from each input, let me do the annotation. See, I'm having here 1, 2, 3. So this is my input,
Yeah.
and this is my
First layer.
first layer, and in first layer I'm having two neurons. Okay.
Yeah.
So from each of my input, it is going right.
Yeah.
So 4W from for this,
Yeah.
right. Similarly, here also.
Yeah.
Okay. So I'm talking about this layer, right, where I'm having total, wait. Okay. So total it 4 input and wait. Yeah, this we're talking about the first layer, right? This one.
You said, right, to ignore that one. You said think about only dense 1, 2, and 3.
Yes. But how the architecture is created is we can ignore it, but model has considered it, right? How our neural network is created is we will have first of all first layer. In that first layer, we will have total two neurons.
Okay.
In the second layer, I am having total two neurons again.
Okay.
In third layer, I am having total four neurons. In and fourth layer, I'm having two neurons.
Yeah.
Right, because I've executed that block, right, where I showed by two steps. That's why one additional layer has created,
Yeah.
and that layer is having total 10 params. So I'm going to tell you how this param 10 came. So you'll have total 8 W's,
Yeah.
right, and you'll have 2B also threshold for each neuron,
Yeah.
right. So total number of learning parameters, how much you are having? 8 plus 2, 10. That's why 10 came.
So that B will be only one, right? That B will be going to one to that neuron as well as to other neuron. Like you have put it showed in like two B's, but in reality, we should just make one circle on the left side that will be like a B, which is going to both, right?
You're saying like this?
Yeah.
Uh,
That's how you were showing in the
yes,
theory class.
yes. So what will happen is, although both the value of B will be same,
Yeah.
right? But it will treat it as a 2
Yeah.
because,
Right.
right? So that's why total number of learning parameter, it is coming 10 here.
Yeah. Okay. There it is coming 10.
Yeah.
Then
Now,
in the second one, it is coming as 6.
yes. Now in the second layer, how many neurons I'm having? Total two neurons, right?
Yes.
So this is going to this. This is going to this,
Yeah.
right? Total 4W
4 W's. Yes.
and 2B.
Yes.
That's why 6,
6.
right?
Then 4.
Then 4.
Uh,
So let me do here. From 2 to it is going 4, right? 1, 2, 3, 4, right? So 2W from for this neuron, 2W
yeah.
for this neuron,
Oh,
right? Total
yeah.
8W
Yes.
and 1B for each neuron plus 4B.
Yeah. So that's going to be 12.
Yeah. And from 4 neuron, it is again going to 2 neuron.
Yeah. So it's going to be 4 and 4, 8, and then 2 B's 10.
Yes.
Okay. Okay.
Okay. It's good that you asked this question because, this is a question which is very frequently asked in interview, and many people, they face difficulty answering this
Okay.
because they know how to use the tool, but they don't pay details about the output of these internals, right?
Yeah. Yeah.
Okay, cool. So we have defined our inputs to compile, right? Now, once we have given this input, the next thing will come is the train module. So training is typically done by something called fit function. Okay. And it will take your input data, right? Here it will take your X, Y. Okay. And once you'll hit this one, it will start training the model.
Y is the target, right? Which
Yes.
we already know.
Yes. Y is the target. Okay. So this is the skeleton of neural network for solving any kind of problem. First of all, you have to define the layers, define the proper activation function, right? Then you need to define your optimizer loss metric, and after that you have to start the training. Any question till this point?
No.
Okay. No. Now there are few things that we should keep in our mind. So now sometimes what happens is if you are training data, if you're training for any problem, sometimes it goes for like forever. Sometimes what happens, the model faces difficulty to find the global minima, so it will keep on oscillating between the points around minima, and you will see that the training process is never completed, right? So for that, there is something called callback function in deep learning. What that callback function says that if you have reached certain level, and after that level you're not seeing any improvement in the model performance, right, then you should stop the training and you should live with the value of W and B that you have received. Otherwise, the training process will go for forever.
So when you say we have not reached the right value, meaning what? Like for example, you have this say a data set, training data of say 10 GB. You put it to training, and it trained for like say typically say it trains for 6 hours, and then it will give us our accuracies, right? In the end.
Yes.
So that means it's done, right? So when you're saying when it is going forever, means it will just continue instead of 6 hours, it will never stop.
Yes, it will never stop. See, what happens is when training, the purpose of your model is to achieve your minimum value, minima, right? Minima of your
Yeah.
W and B.
Yeah.
Right. So let's say that this is your W, and for some initial value, this was the W you have initialized, right? So it will
Yeah.
keep on training until it reaches to this point. What I'm saying that there may be situations that you never reach this point. When it can happen, first is if you have set these steps, the learning rate very, very small. If you have set learning step very, very small, it will first of all go from this point to this point, this point to this point, this point to this point. Since you have taken a very small learning rate, it will take large amount of time to reach this minima value.
But it will, right? Like it
It
cannot be
will,
forever, right?
but you cannot wait for weeks, you cannot wait for months, right?
Yeah, that's true.
So that is the meaning of forever. When I'm saying it is forever. Okay. The other thing that may happen is, suppose you have defined a very large value of learning rate, right? So it will start from here, it will start here, it will jump to this point, then it will jump to this point because you have defined large value of learning rate. You'll this way, this, and after that it might overshoot your minima and it will jump to this way. Okay. then it will say, oh, I have overshot the minima, let me go back. It will again come back to this point. It will
So
say,
how you will know that you have overshoot the minimum? Like what will tell us? What will tell it?
that can happen if you plot the graph. If you
Okay.
plot the trajectory of your W, now you can see that it has overshot the minimum value. Again, it will come back to this point. It will again go back to this point. It will keep on oscillating around minima, right? So it will never stop in that case also.
So when you say we will know it by looking at the graph, meaning I will see this graph, which is like a U, right? Like a parabola, and the graph will be extending beyond that minimum point. Like it
Yes.
will be start going up. So is that an indication that it has missed it?
Yes, yes, that is precisely the indication. But visualizing this graph is also not possible, right? Because right now I'm just showing it for one value of W. If you are dealing
Yeah.
with very high dimensional data, it will be high dimensional figure.
Correct.
Right. So the best way that we can get make a guess here is, if we don't see improvement in performance, that means we'll make an believe that maybe we have defined a very small value of learning rate, or maybe our value is oscillating between smallest value between the optimal value of W, right? So in
Correct.
that case, what we'll do is we will stop the training, because we know that we have reached very close to minimum, just that we haven't got the optimal value. And in most practical situations, you can live with that.
Okay.
Right? It's okay if you are getting, instead of getting 95% of accuracy, I'm getting 94% of accuracy.
Yeah.
Right. So that's why there's something called callback. Right. So callback, what it does is it set a system in your optimizations in your training, that if you don't, where you continuously monitor the performance of your model, you keep on making a track of your loss, decrease in loss. If you'll see that your loss value is not changing, your loss is not further decreasing, right, then it will stop the process. The callback function will stop the training process, and it will give you the value of W and B which was there at that point. Okay, is this concept clear?
Can you explain the callback once more?
See, callback is nothing but it's, you can think as it as a helper function. What it does is it keep on tracking your value of loss until it sees that there is substantial decrease in the loss. It will allow your system to do training.
Okay.
Once it sees that your loss is not further changing, the loss is not further decreasing, then it will stop the training process and it will give you the value of W and B, which was there at that point of time.
Okay, so the callback function is just helping us in getting the optimal value of W and B when in cases where it is going forever.
Yes.
Or it is oscillating.
Yes.
It is like it is aiding us in getting the optimal value.
Yes. Yes.
Okay.
Yeah. Okay. So we are having a module for callback. So typically in callback, we are having a lot of functions. What function that we're gonna use is called early stopping. Early stopping is something that will do the things that we have just spoke about, right? It will just keep on tracking the value of your W and B, sorry, loss. Once you see that the loss is not changing, it will stop the process and it'll give you the value of W and B. Okay.
Okay.
So from tensor flow dot keras dot callbacks import early stopping. Okay. Now I need to instantiate this early stopping. Monitor. So we want to monitor our loss, right? That's why loss. Then I want to wait for 5 iterations. I'll tell what is my patience here. Okay. Yeah. So here monitor means it will keep a track of loss. Now patience is what? Patience is, let me do my notations. Yeah. So in every iterations, you should see some decrease in loss,
Yeah.
right? So it will keep on, the loss will keep on decreasing. Now what it will do is, if you see there is no decrease in loss for consecutive 5 iterations, in that case, your training process will stop, right?
Yeah.
So that is I meant by saying patience. Patience means the number of consecutive iterations you will wait, you will watch, and if you don't see any improvement in performance, then you will stop the training process. Okay. There is another parameter which is called restore best weight. Restore best weights. If you keep this as true, it will return the best value of parameters that you had by that time. Okay.
So that if you're giving that value, if you're giving restore best weights, then you should not give patience equal to 5, right?
No. Restore patience equal to 5. It means it is waiting for 5 consecutive iterations. And if it doesn't see any improvement, it will stop the training. Now, once you stop the training, you have to provide the value of W and B, right?
Yeah.
So if you will do this restore best weight, it will provide the best value of W and B you had by that time, by the time you stopped the training process.
But even if you don't give it, will it not be the last value of W and B, which when we've set the patience equal to 5, where the loss is not improving, so it will keep a track of that W and B, right? And it should throw that W and B, right? Why do we need this restore best weight? That means there can be different values of W and B where towards the end they are satisfying.
Yeah, I'll answer that question. So I understood your question. See, let's say that my last 5 iteration is something like this. It is very close to minima, but then it has overshot your minima and it has reached here.
Yeah.
Okay. And it realizes that it has overshot your minima. It will come back. It will try to come back. It hasn't reached the minima yet. Again, it will approach to a minima, and again it has overshoot. Right. And now you see that, so in this case, your patience was 3. That's why at this point you stopped your process, because you are seeing that your loss is not reducing, right?
But why will it shoot back, Ashutosh? Like, why will it go back?
Yeah,
It
because
should.
because what, if you recall the theory, what we learned is you should always move opposite to the gradient,
Yeah.
right? At this point, what is my gradient? My gradient is this, right? It
Yes.
should go
Yes.
back. That's why it will come back.
Oh, okay. Okay. Yeah.
See, everything is connected. Whatever things that we have learned in theory, everything you see the applications in practical,
Yes. Yes. Yeah.
right? So
Yeah.
now if you'll take now if you will take this value of W, obviously it is not the optimal value. The optimal value is somewhat here.
Correct.
So what it does is it keeps a track of all the loss and all the value of W and B. And instead of giving you the last value of W, B, and B, it will give you that value of W and B for which your loss was minimum. So instead of
Oh.
giving this W and B,
Yeah.
it will give you this value of W and B. Okay.
Wow, that is amazing. I mean, how the theory is perfectly fitting in what you're saying now.
Right. Yeah.
Yeah.
So yeah. Now sometimes what happens is this may be, so if we'll do this parameter, if we'll keep it as true, now this will be a somewhat an overburden for system also. Sometime it may happen, right? In that case, you need to create another data structure which will keep a track of your W and loss, right?
Yeah.
So that will add some amount of more computation complexity. That's why people prefer to sometimes they prefer to keep it as false. Hello.
Yeah.
Yeah. So sometimes they want to keep it as false, and they just simply says that I don't want to go to this level of complexity, just keep it the last value you had before you stop training. You can keep this as false also, which might increase your training time, but obviously you'll have a one trade-off. You might not get the best value of WNB, but in practical time situations it may be okay.
But does that, like, just adding, removing that one flag
Hmm.
significantly reduces the training time? Like, it's just one flag, right? How can it impact training where we have to do this trade-off?
Yeah. See how it will impact is, now if you have kept this flag as true, now the system has to keep the record of your loss also and their corresponding W and Bs also,
Yeah.
right? And just think that you have to perform these iterations for at least 10,000 or 20,000 number of times.
Okay. Yeah.
So
Then
those,
it increases.
yes, so those small incremental change, if you'll compound it creates sometime a substantial amount of time every, although in one iteration it will hardly create a difference of some millisecond, but if you'll do it for 10,000 times, those things will become like 2 to 3 minutes.
Yeah,
Okay.
that's correct.
So yeah, so that's why Keras is providing this as an argument, and you have this option to keep it as true or false. Okay.
Yep.
Yeah, so that's all we have as a foundation for creating any neural network. When I'll take one specific example, I'll show this entire process in that data set, and from end to end we will see how do we start with one specific data set, apply this neural network and get the accuracy at the end, right? But these are the different bits and pieces we have, and we need to stitch them together to solve a problem,
Okay.
right? So let me summarize this for you once. Can you summarize it for me? That will help you to consolidate your learning also.
You mean summarizing the whole skeleton?
Yes. What are the things that we have captured in today's class?
So the first thing we have captured, we have understood is about the, the model module, which, like, what kind of
Mm-hmm.
model we're using, right?
Mm-hmm.
And then uh, the layers
Mm-hmm.
and activation function that we are going to be using.
Mm-hmm.
And then can you go down? So we have yeah, after that we are going to be using this optimizer module,
Mm-hmm.
which is going to give us the information about how we are going to optimize our WNB.
Mm-hmm.
And here in this case, the optimizer we are using is stochastic gradient descent, which we saw in our theory when we were understanding. And there can be
Yes.
different optimizers, not just that, right? And
Yes.
then the loss function that we are going to be using will be sparse categorical cross entropy.
Mm-hmm.
And the metrics, meaning how we are going to be measuring the output, is going to be based on accuracy.
Mm-hmm.
And then we are using callback module. In that callback module, we are using early stopping function. Basically, we are using callback is to because sometimes what happens is that your training can go on forever,
Mm-hmm.
meaning for a very very long time. And so in order to get the right value of W, we will be stopping it, and that stopping is done using by this callback module, where we are monitoring the loss, because for every iteration the loss is changing or reducing.
Mm-hmm.
And then we will give this patience of 5, meaning during the, say, the last consecutive 5 iteration, if the loss has not changed,
Mm-hmm.
uh, or something you said, I'm not able to recollect.
Mm-hmm.
But then we also have this other flag, restore best weight equal to true,
Mm-hmm.
meaning in that last 5 set, because as you explained, that the grade, the iteration where it is very small, but then it
Mm-hmm.
overshoots the minima, so it
Yes.
can take that long step, and then it will again go back, because the gradient cannot, gradient, it has to go always against the opposite. So now we have different set of W and B, and this will capture the best fit
Correct.
for the W and B. That's why we are giving it. But then there is a trade-off for it, that is it may increase the training time. So in some cases we don't use it, and the last five it will just take some random value, I guess, or whatever was the last one, it will just pick that. So it will impact the our value of WB, but still we get something of some
Yep.
accuracy.
Yep. Nice. Yeah. So thanks. That shows that you have able to take it really well. Uh, that was the previous agenda I had before the class. So we are
Oh yeah,
familiar.
but Ashutosh, we have never used this OPT equal to SGD learning rate, right?
OPD is equals to SGD. Yeah, actually, the sigmoid learning algorithm, that is nothing but it is SGD only. So we have crafted this algorithm. If you look at the slides, I have sent you the code for SGD also.
No, but here where are we using it? We are not
Yeah,
using the OPT variable.
yeah. So when we will do this model dot fit, you know, model dot fit, and I'll put X and Y. Then whatever thing that we have defined till here, right?
Mm-hmm.
Right now, just model has kept a record of it. Now, when you will start the training, it will refer this manual, and
Yeah,
based on this constraint, it will do the training.
yeah.
Okay. So
No, but
until Mhm.
yeah, but then will we be using that OPT equal to SGD OPT variable in the future somewhere down?
No, because we have already specified here also, right? So I was just showing you there's a one way of specifying SGD in this way. There's another way of specifying your optimizer in this way also.
So, but in the other way, which is where you're just you're doing OPT equal to SGD,
Mm-hmm.
and inside there's a learning rate of 0.01. So
Mm-hmm.
that one is not specifying, what optimizer it is, what the loss is, what the metrics are, right?
Yes, yeah. So here I was just showing that uh, the loss function as an individual entity, right? But here what we are doing is we are tying this loss function, sorry, optimization functions with multiple entities.
Hmm.
Are you able to understand?
No.
No, okay. Let me rephrase this in this way. Like the way we have seen earlier, like for layers, there are two
Yeah,
options you are having. One is you can do everything in one step. The other is you can have everything in separate step, and you can at the end you can tie them together.
yeah,
Right? So similarly, here also we are having. Here we can first of all we can define our optimization step, optimization statement. After that, I'll define loss statement. After that, I'll define a metric statement, and after that, I'll finally stitch them together.
yeah.
Right. So that is
So
a
that stitching together is on top, learning rate equal to 0.01.
no. You forget about this two line, right? So that was only with an intention to show that there's a SGD function we are having within optimizer module. Okay,
Yeah.
these two steps you it will not be there in flow. See there
Okay.
are yeah
Yeah, this is clear. Like,
yeah
I think now I understand. If you have removed them, then it's clear like what is going on.
yeah yeah yeah.
So one question I have, Ashutosh, here, that whatever your strings you're giving within the double quotes, right? Like for
Mm-hmm.
example, you give loss, then
Hmm.
you give accuracy. So are these like strings that the Keras and TensorFlow has defined them?
Yes. In fact, when
For
you
example,
pass
if I
this,
put LOSSE,
mm-hmm.
I should get some error, right? Like I should get a syntax error saying that, oh, it does not understand what you're saying to monitor.
No. See here, these are my positional argument, right? So whenever you
Yeah.
do optimizer equals to SGD, it precisely understand that you're talking about stochastic gradient descent optimizer.
No, but if you give SGDE, what will it understand as?
It will give an error because
It will give an
SGD,
error, right?
yeah, because it doesn't, because it's nothing like SGDE,
Okay, okay.
right? So
Yeah, that's
these,
what I was
yeah,
asking. That those are like defined already, right?
yes, those are defined.